All right, let's talk a little bit about molecular orbital theory, and we'll talk about these molecular orbitals being probability functions. So when they overlap to form chemical bonds, that probability function changes, and we call them molecular orbitals, or MOs. So the molecular orbitals belong to the molecule as a whole instead of any individual atom. And so the waves that describe these atomic orbitals have positive and negative phases or amplitudes. They can interact constructively or destructively, just like any other wave. So we have in-phase overlap, where the wave gets bigger, and then we can get out-of-phase overlap, in which they destruct or subtract. In this case, they completely subtract, and that's something we call a node, where you have zero probability. There are some simple types of overlap that we'll talk about. And head-to-head overlap produces sigma orbitals, which are your sigma bonds. And side-to-side overlap of atomic orbitals produces pi bonds. Those are going to be present in double and triple bonds. Also, we have bonding and anti-bonding orbitals. The electrons will fill the bonding orbital first, and then the anti-bonding, and then if the anti-bonding is completely full, it will cancel out the bonding completely. The anti-bonding has a little asterisk, and that indicates the anti-bonding for that particular orbital. So graphically, it would look like this for s orbitals. If I got one s orbitals, out of phase, there would be a nodal plane between the two, meaning that there is no bond. The orbits or orbitals are separate. Where if there's a bonding in phase overlap, you get a chemical bond, as you would say for a hydrogen molecule. So if we look at it for a 1s lies at a lower energy, sigma 1s, sigma 1s star, the antibonding orbital is a higher energy. So if we look at that simply, where we got a 1s, and this that first orbital, and a 1s, this is my sigma 1s and my sigma 1s star. If it's, let's say we look at H2, you have one electron in a 1s orbital for each hydrogen atom. When I populate that, oops, I need the opposite spin there. We've got a paired set indicating one sigma bond. And so when we draw our hydrogen molecule, that one sigma bond is what connects the two hydrogen atoms. Now, what if we upgraded that and went for helium? We'd have a matching set now on both. So not only would I fill the sigma 1s, I would fill the sigma 1s star, indicate, and the 1s star cancels out the sigma 1s. And so I would predict that there is no helium molecule. That doesn't exist. And we predict that that doesn't form, and it in fact does not. You can have head-to-head overlap of the two corresponding p atomic orbitals, say in a 2px. That's generally the one we consider to be a sigma overlap. And you can have an anti-bonding orbital. Again, you've got the node in there and the bonding section between the 2p orbitals, if we have a bond. The 2py and 2pz are side-to-side overlap, and so you got a pi 2py and a pi 2pz, but then you've got a pi star 2py and a pi star 2pz, which are your anti-bonding orbitals. So looking at that, what we can see is that we kind of get them sort of scattered to the wind here with a big node in the middle. But here we see overlap above and below, or not as obvious. If it were the other one, it would be to the front and the back, which is harder to picture, which is why you don't see more than a triple bond. If I got two atoms, say two carbon atoms, the single bond is a sigma. You've got a double bond there, which is pi on the top and the bottom. And then I'll do this in a different color in red. And then you're going to have, and then it's hard to draw, but you got one to the front and back. And so the order of filling of this follows the same rules as atomic orbitals. In the Aufbau principle, you're going to fill the lower energy first. And you got one molecule for hydrogen through nitrogen, and then another diagram for oxygen, fluorine, and neon. So if we look at these diagrams, they're more or less the same, except once you get up into these P overlaps, you can see it's in a different order at that spot. So you have to use the diagram that goes with the one that you're trying to draw. Hydrogen to nitrogen is A, where the sigma is a higher energy bond and the pi's are lower energy. And then the oxygen through neon, where that is reversed, the rest of it being the same. And so what we would do to determine the bond order, that is whether it's a single, double, or triple bond, we take the electrons in the bonding orbital, subtract from it the electrons in the antibonding orbitals, and divide by 2, and that would give us our number of bonds. If that bond order is 0, that means we predict that that not form a molecule, as in the case of the He2 we talked about before. Greater than 0, like 1, 2, or 3 would imply that you have a single, a double, or a triple bond. And we're going to focus on diatomic elements for this discussion. So let's take a look then. Here's one for nitrogen. So let's block in the atomic orbitals. Then we got 1, 2, 3, 1, 2, 3. Those are my orbital diagrams. Let me go ahead and zoom just a little bit more. So looking at it, down here, I've got enough to fill the bonding and the anti-bonding. So no bond there with the 1s. It's not in the valence shell, so I wouldn't expect it to. But the same with the 2s. The 2s's aren't bonding. So my bonds must be happening up there in the 2p. So I've got 3 6 electrons, so it's going to be 1, 2, 3, 4, and then 5 and 6. And I don't have any in the anti-bonding, so my bond order is going to be 6 electrons minus 0 divided by 2, or 3. And that's exactly what we'd predict. If we draw a nitrogen structure, as we've drawn before, that's a proper structure for nitrogen, which has 3 bonds or a triple bond between the 2 nitrogens. It gets a little bit more complicated if you do heteronuclear diatomic molecules, which we won't focus on in this presentation because the energies of the orbitals are not quite the same. More electronegative elements tend to be lower energy than the less electronegative elements. But one place where the molecular orbital theory does shine is structures where you have resonance. And I mean resonance structures where they're equally likely. We did talk about some structures before that may not be as equally likely. But we talked about the fact that these bonds here, we're just moving around the double bond, but we said that the structure was really more like a bond and a third in each place where the electrons are shared throughout the structure. Well, it's hard to draw that with a Lewis structure. These delocalizations of electrons is predicted by molecular orbital theory. And if we look at our friend carbonate, we see that the electrons are shared throughout the structure. We call that a sort of the pi bonding network. So those double bonded electrons are shared throughout the structure, indicating a very stable structure. Same with benzene that we talked about exhibiting resonance. And if we draw a traditional Lewis structure, we see alternating single and double bonds. But in molecular orbital theory, we show those electrons shared throughout the ring. So this is the case. These are cases where molecular orbital theory does a better job than Lewis structures. And that'll conclude our discussion of molecular orbital theory.